I am Bursa. I am a World Heritage Site from the depths of history. I am a depository of civilizations on the foothills of Mount Uludağ. I am the ancient capital of the Ottoman Empire and its enduring spirit. I am Bursa. I am the prayers and calligraphy of the Ulu Mosque. I am the tiles and ceramics that give the Green Mosque its name. I am the houses of worship in Iznik, once home to Romans, Byzantines, Seljuks, and Ottomans. I am the Muradia Mosque complex, where life and death, dreams and reality, poignance and joy are contemplated. I am a boundless land of legends, the living cultural heritage of Cumalicuzic, the sun setting on Gölyaza Lake. I am nature's gift to humanity. I am the color green in all its shades. I, a centuries-old sycamore, tones of blue and green, sun and lake, am Bursa. I am the eternal beauty of the Longos forest. I am the rushing waters of the Sai Tabat and Suuchtu Falls. I am a city of flavors, where history meets gastronomy. I am crispy jontic from a wood-fired oven. I am the finest olives and olive oil. I am the birthplace of Bursa kebab. I am köfte with pide and inegern köfte, that is, a paradise of Turkish-style meatballs. I delight palates with sensational flavors, like soft tahini pide and candied chestnuts. I am a land of fresh fruit and nature's bounty. I am paragliding between sky and forest. I am the center for adrenaline and nature sports. I am the timeless shadow puppets, karagas and hajavats. I am handicrafts at Erkan Bridge, a steel knife forged in fire, a smooth silk shawl from Kozahan, a handcrafted Iznik tile. I am the last stop before Europe on the Silk Road, the covered bazaar. I am so much more than a city. I am Bursa.
Dear colleagues, dear participants, dear guests, welcome to station 15, entitled Antennas. In this session, we have 5 papers for presentation. The first paper is entitled Microstrip Patch Antenna for a WLAN Receiver. I suppose it will be presented by Funda Cirik. You can begin your presentation.
Okay. Hello, dear Professor Afacan and dear other participant. Before the begin, I would like to thank the Chamber of Turkish Electrical Engineering Bursa branch and other organizer university for this conference. My name is Funda Cirik. I am research assistant at Marmara University Electrical and Electronics Engineering Department. Our accepted work is about a microstrip patch antenna for a WLAN receiver. In this work, we are together with Professor Yıldırım, and this is my presentation's outline. After the introduction, I will mention about the design procedure, and I will show the designed and fabricated antenna. Then I will give a comparison of measurement and simulation results, and I will finish my presentation. And the aim of our work is to design any microstrip patch antenna for a WLAN receiver. This designed antenna operates 2 different frequency bands. They are 2.45 GHz and 5.2 to 5.9 GHz Wi-Fi bands. Designed antenna is composed of a metallic radiating patch, and on the above, a dielectric substrate backed by a ground plane. 1.5 mm thick FR4 substrate was used because we know that FR4 performs well up to several gigahertz, and it's a low-cost material for the antenna design. And some electromagnetic simulation softwares like that HFSS, Ansoff Designer, and Smith software were used to optimize the design. And in this slide, you can see the basic geometry of the designed patch antenna. We have chosen a square patch, and its dimensions of the square patch as 28 mm for width and length. And the ground plane dimension are selected as 100 by 100 mm square. On FR4, you can see a transmission line. This line, a 50 ohm line, and should be about 3 mm wide. This width is calculated by Ansoff Designer. And this line's length is 36 mm. And that's connect to patch, and its practical width is 2.8 mm. Because HFS simulations gave about 50 ohm characteristic impedance for 2.8 mm. And the copper thickness for all conductive part is 35 microns for all other simulations. And now you can see the basic simulation results. It's observed that S11 is about -6 dB at low frequency, 2.5 GHz, and -12 dB at 5, and -9 dB at 5.65 upper frequency band. We have obtained the simulation results, and we have observed that the low band is nearly at 2.45 gigahertz, but the upper frequency band needs to be adjusted. We have to obtain the desired bandwidth. So we determined that the square patch antenna is not well matched. To obtain the desired upper frequency band, some parts have been cut from the patch antenna, because we know that extracted or added parts to the antenna affects the bandwidth. So some parts from the patch left and right sides have been cut. In this time, we have made a parametric study, and we have obtained the results. And the results show us that the desired optimization can be achieved in non-symmetrical right and left cutting situations. This geometry in figure 3 gives us the best performance. In the geometry, the right and left cuts have been located on 2 millimeter up and down from the center of the patch edge. And the dimensions of the cuts are 2 by 12 millimeters. And figure 4 shows the S11 results of this asymmetric geometry. In here, upper bandwidth can be seen on the figure at marker M4 and M5. When we draw a horizontal line from the minus 10 dB S11 value, upper bandwidth is under this horizontal line. This is a good situation. And marker M4 is at 4.5 gigahertz, and marker M5 is at 5.85 gigahertz. Therefore, this geometry gives us the excellent result to achieve the wider upper bandwidth from the 5.2 to 5.8 gigahertz. The bandwidth is about 700 megahertz. And also the antenna has two new operating frequency. And until here, the designed receive patch antenna has the strong and wide upper bandwidth optimization, but weak low band optimization. After that, we was focused to optimize the lower frequency at 2.45 gigahertz. To operate perfectly, S11 results, we know that S11 results have to be below minus 10 dB. As you can see, our low band S11 response is minus 6 dB around. The reason of this, again, the receiver patch antenna is not well matched. To match the antenna impedance to 50 ohm and obtain a better S11 results, a matching circuit is needed, and we have to calculate the real input impedance of the antenna. So we checked the Smith chart, and we checked the Smith chart, and this figure shows the S11 response on Smith chart as seen from the SMA feed port without the matching network. And M1 marker is indicated at this point. In this point, antenna input reactance is capacitive, we can see, and normalized and denormalized impedance value are written here. And we have determined a matching circuit, and the matching circuit is implemented 2 millimeters before the antenna. So the antenna input impedance ZA has to be the real antenna input impedance has to be calculated by subtracting a length of 34 millimeters. The electrical length, we found that we know that beta L of this long microstrip line is calculated as 173 degree using Ansoff Designer software. Then we have utilized this value. We consider that the antenna is a load and a move of 2 beta L amount degree towards the antenna on the Smith chart in the counterclockwise gives the value, the real antenna input impedance. Shortly, to bring the input impedance to point 2, point B must have been shifted 2 beta L. 2 beta L is 367 degree, or simply a 7 degree on Smith chart counterclockwise. And now we obtain the real input impedance antenna starting point ZA we found. And in this figure, ZA is shown as 0.1 in this figure. To transform ZA 50 ohm without distorting the upper band, a matching network is designed. In here, points 2 and points 3 are on the VSWR circle, which correspond to about minus 10 dB. And it was possible to get close to this circle by using inductors, shunt inductors. We have tried, and adding a shunt inductor would move the impedance from 0.1 to 0.2 or 0.1 to 0.3, depending on inductance value. And these values are calculated to 6 nanohenry and 3 nanohenry shunt inductors respectively. And in the theoretically, a grounded and narrow microstrip line was used as a shunt inductance, but in our practical design, instead of a narrow microstrip line, we have used 2 grounded and narrow microstrip line, and the length of each microstrip is chosen 4 millimeter, and both are 3 millimeter wide, and they were terminated by a shorted load. And you can see the figure 8. A matching network is both sides of the microstrip line. And figure 9 gives us the simulation of the proposed patch, which has matching network. It can be seen that the low band is at 2.5 GHz, and the high band starts at 5.2 and it ends 5.9 GHz. This overall design now gives us the best situation for the lower and upper bands. Then we fabricated the patch antenna, and you can see the fabricated patch in the figure 10, and the matching network indicates on the figure. Then measured S11 response of the fabricated patch antenna is shown in figure 11. Low band and upper band can be seen clearly, and measurement and assimilation results are in a good agreement. S11 response, antenna radiation pattern measurements at specific 2D planes and gains of this designed antenna at the operating frequency were obtained at the TÜBİTAK Bilgem Antenna and Test Research Laboratory. And table 1 shows us measured and calculated antenna gains at these frequencies. Gains may be worked again. We may develop the gain value by adding a parasitic patch on this design. We will focus on this design next work. Then we have obtained the measurement, radiation pattern measurement, and we have compared radiation pattern measurement and simulations. And again, these measurements are performed at TÜBİTAK. Now you can see the 2.4 GHz in X, Z, Y, Z, and XY plane. We can say that the simulations and measurements are in a good agreement. There is not much radiation behind the ground plane. And this is for 2.5 gigahertz and for low band. And this slide gives us 5.2 gigahertz results. Again, the comparisons are good. 5.4 gigahertz results for upper band frequency, and 5.6 gigahertz result. And finally, we have 5.8 gigahertz results in 3 dimensions.
Excuse me. We have nearly completed 20 minutes.
Okay.
Can you be
okay?
faster?
And I am finishing, and the last slide. In this work, any multiband and single port microstrip receive patch antenna is designed. Antenna has 700 megahertz bandwidth at the upper band due to non-symmetrical cuts, and a microstrip matching network to obtain a better response for low band, having virtually no effect on the upper band. These two are the main approaches of the presented antenna, and measurements and simulations are shown to be in a good agreement. And these are our references. It's the end. That's all I have to say. Thank you for your participation. If you have a question, I can give.
Thank you for presentation. You can ask some questions, if any.
Hello.
Hello.
Many thanks for your presentation. I have just one question. Could you please, in just one sentence, that remind us what's the contribution of your work?
Actually, this is an active antenna design part, and this is a receive antenna, and this work is a part of my PhD thesis, and I am continuing to develop this work. Now I am designing the transmit antenna. So this is a main work for me.
Because I see that the design is so simple. That's why I think that what is the contribution and novelty of this work? I think that from my point of view, you have to develop the configuration a bit more complex. It's my opinion.
The main approach, the main points, this antenna is upper band, wider bandwidth value, and the new matching network part. The adding new matching pattern network part.
Okay, wish you luck.
Contributor. Thanks.
Thank you.
Thank you for the question and comments. Any more question? Okay. Thank you for presentation.
Thanks for you.
Our second paper is entitled Conjointly Electromagnetic Simulations for Banded Microstrip Designs.
Yes,
I suppose it will be presented by Lida. Please.
Yes, thank you very much. Now I am starting. Could you please see my screen?
Yes, we can see.
Okay, good. Hello and welcome to everybody. My name is Lida, and right now I am as the assistant professor at Doğuş University in Istanbul. This paper is with collaboration of dear professor Dr. Ladislau from Politecnico di Torino in Italy, and also dear professor Dr. Serdar from Istanbul Technical University in Turkey. This paper presents the conjointly electromagnetic simulations for banded microstrip antenna designs. Firstly, I will give a short introduction, then I will talk about the antenna designs, simulation results, and also the conclusions. Biomedical devices are really important components that has been effective at our daily lives. For example, in our wearable watch, we can see that, and it's very popular. It has been published from various marks. We can see that we can also calculate the heartbeat, so we can measure the temperatures of our body and many other applications. Or for example, in the second image, you can see that he is the deaf in the colors, and by using the medical devices, he can now see the colors. And in the third one, we can see that there are variable devices that can be used, for example, as the heat and etc. In medical devices, materials are really important to be used to get the effect of biomaterials. There are various types of biomaterials, such as the synthetic and natural polymers, metals, ceramics, compounds. And here we have to pay more attention significantly to the performance, to the structures, properties, because they are used inside of the body or outside of the body. And here we are talking about the life of people or persons. So we have to pay more attention to the materials that we are using. Medical devices are devices or tissues that are positioned inside or on the surface of the body without exactly affecting the quality of the life. So medical implants functions can be a substitute as a missing parts of the body, or they can provide support to the organs and to the tissues. Nowadays, for example, implanted teeth has survived many people's life, even though it's expensive, but I think that it deserves, because they are putting as the natural teeth of the patient people. Here in this paper, the target is firstly modeling the antenna by using a bottom-up optimization in the ADS. And then we would like to bending the microstrip antenna using the bend shape function in the CST. So here we are using two different softwares as the ADS and CST in order to design and optimize the bended microstrip antenna. Okay, firstly, we start using a bottom-up optimization. What's the bottom-up optimization? It starts with a smaller part and then larger to the large sections. So here we are using just one transmission line, and then we are constructing the large microstrip antenna using various transmission lines. And then after that, we are getting the layout from the ADS and then transferring the layout to the CST environment and using the bend shape function in the CST environment in order to bend our microstrip antenna to be used as the wearable devices. Oh, sorry. Okay. This is our design and optimized microstrip antenna. As you can see here, we use the Rogers here with a specific, specifications such as the tangent and epsilon r, and the thickness of the 1.52 millimeter. And then these are the sizes that you can see here that has been optimized using the bottom-up optimization. We use the coax feeding here in order to biasing our microstrip antenna. After that, we get the layout and insert it to the CST environment in order to bend our antenna to be used as a variable devices. Here we use the bend functions and we bend as a 45 degree. This is the S11 simulation results of our microstrip antenna that, as you can see, after bending, we have a wideband from 8.9 to around 9.5 gigahertz. These are the radiation patterns of the bended microstrip antenna in both of the planes, in the H planes and also in the E planes for the various frequencies such as the 8.8, 9.1, and 9.4 gigahertz. Okay. We can conclude our contribution like this, that really EM simulations in the microstrip antenna design is really time consuming and it needs a various and additional efforts. This paper presents a new method for designing banded microstrip antennas where the pulse layouts can be generated with a reduced effort. And firstly, we configure the microstrip antenna using a bottom-up optimization in the ADS environment, and then we use the CST environment in order to bend our microstrip antenna. This methodology provides a ready-to-fabricate layout, more easier than the initial configuration that's generated by the other softwares. Thank you very much for your attention.
Thank you for presentation.
Thank you.
It has been very short and very concise.
I think that it's okay for you because the last one was so long, that's why.
Okay, thank you. Any questions? We have time for questions, if any. Since there isn't any question, then I can ask you, I wonder, how did you obtain the shape of the antenna? How did you think? Because it's interesting. Okay. It's not usual.
Okay, so let me go to the first here. Okay, Professor, here, this is the bottom-up optimization. Firstly, we start with just one transmission lines that includes the various widths and lengths. And then sequentially, we increase the number of transmission lines in order to configure our configuration and topology of our microstrip antenna. Is it okay?
Okay. Thank you for presentation.
Thank you very much. Have a nice day.
Thank you. Our third paper is entitled All-Textile, Washable Metasurface Antenna for WLAN and mid-band 5G applications. I suppose it will be presented by Esra Cirik. You can begin your presentation.
Hello, dear professor and dear participants. My name is Esra Cirik. I am PhD student at Yıldız Technical University and I am lecturer at Maltepe University. Author paper, author name is Professor Dr. Nurhan Turker. She is professor at the Yıldız Technical University. Also, she is my supervisor, PhD supervisor. My presentation consists of 4 parts. I will start with introduction, then I will continue metamaterial unit cell design, antenna design and discussion, and conclusion. In the last slide, variable antennas that are used in many areas such as health services, military application, public security, location tracking, communication in harsh conditions have received a lot of attention. They offer small size and low-cost antenna for 5G technology due to being flexible, light, and easy adaptation to moving human body. Textile antennas protect user comfort. Textile antennas form the basic radiating element for WBAN technology, which is popular worldwide recently. Besides variable antennas, WAN can be used in high power IEEE 802.11 WLAN application. With WBAN technology, the use of wearable electronic devices in the field of health has become widespread. WBAN technology able monitoring patients' health parameters such as heart rate, blood pressure, glucose level, and body temperature. 5 GHz can be used in WBAN, WLAN, and mid-band 5G antenna application. Mid-band 5G frequencies cover the frequencies between 3 GHz and 5 GHz. Mid-band frequency of 5G frequency show difference between countries. For example, mid-band 5G frequency range is 3.55 to 4.2 GHz in USA, whereas it has two ranges of 3.3 to 3.6 GHz and 40.8 to 5 GHz in China. 5G technology includes spectrum in 3 fundamental frequency ranges in order to provide wide coverage and supports all use cases. These 3 ranges are below 1 GHz, 1 to 6 GHz, and above 6 GHz. It is thought that sub-1 GHz frequency will support wide coverage in urban, suburban, rural areas and helps support Internet of Things services. It is predicted that between 1 to 6 GHz frequency range will provide advantages in terms of capacity and coverage. Electronic threads, E-threads, have been introduced for textile antennas due to their flexible and strength. E-threads based on automatic processing system have much better strength than other alternative textile conductors such as conductive tape, screen printed silver nanowires. Most of the textile antennas employ flexible dielectric substrates such as fabric, jeans, cotton, polyester, and film. The loss tangent of pure polyester has the lowest value, whereas cotton has the worst performance. Metasurfaces are two-dimensional variant of metamaterials that is non-existent in nature. The electromagnetic properties of metamaterials are artificially produced. Metasurfaces have many advantages in controlling the amplitude, phase, and polarization of electromagnetic waves. Besides, it is used to enhance antenna gain. Scattering resonator SRR can be used as the main element of metasurface. SRR structures generate a left-handed medium that exhibit negative permeability index at the required frequency. In this work, an all-textile antenna consisting of metasurface arrays operating at 5 GHz frequency is designed. The dielectric materials of the designed antenna is polyester. The dielectric constant of the polyester fabric is 1.9 and its loss tangent is 0.0045 at 2.44 GHz. Different metasurface array consisting of 4x1 and 4x2 SRR are placed on the antenna surface, and their performance is observed with a full-wave electromagnetic analysis tool. The left-handed features of SRR unit cell was provided using the HFSS program. CST program was used in all other analyses. Now I will talk about metamaterial unit cell design in this part. SRR structure was used in the design of the metasurface. Figure 3 shows geometry of the proposed metamaterial unit cell. SRR printed on one side of the polyester substrate with a thicknesses of 4 mm, relative electrical permeability 1.9, relative magnetic permeability 1, and dose tangent 0.0045. Silver coated thread that can be washed with mild detergent 30 centigrade degree is used as the conductor of the antenna. Usage of E-thread offers high conductivity for electrical constant and connection. E-thread is high conductive thread whose resistance is smaller than 300 ohm millimeter. E-thread can be easily embroidered on polyester with an embroidered mesh. The area of the design SRR structure is 12 mm times 12 mm. The size of the ring on it has the parameters of the embroidered with silver E-thread. The distance between ring width and split is 1 mm. Dispersion diagram for the SRR metasurface is obtained with a single unit cell. The boundary conditions of the unit cell are chosen as perfect electric conductor in the X direction and perfect magnetic conductor in the Z direction. Those scattering parameters below the diffraction frequencies are evaluated. PEC and PMC are characterized by varying tangential electrical field and magnetic fields at this surface respectively. The effective medium parameters of the periodic structure are extracted by using the Nicholson-Rosevear technique from the scattering parameters. Constitutive parameters of the SRR unit cell are demonstrated in figure 4. All the electromagnetic constitutive parameters are negative at 5 GHz. Hence, this structure can be used as negative reflective index metamaterial in all-textile antenna operating at this frequency as shown with red dash line in figure 4. As can be seen from the electrical permeability, magnetic permeability, and refraction index, variation of the unit cell as function of frequency. The design unit cell exhibits left-handed metamaterial characteristics between 3 GHz and 6.2 GHz. SRR cells are arranged in N arrays from the create the metasurface. Design metasurface is added the plane of the circular patch. A circular patch whose physical size is chosen to radiate 5 GHz is designed on 4 mm thickness polyester substrate material. Electrical properties of silver E-thread is used. Usage of polyester and washable A-threads constructs a washable textile antenna. The all-textile circular patch antenna is shown figure 5. Coaxial line feed is used for the excitation of patch. Reflection coefficient variation of the all-textile circular patch antenna is in figure 6 as the frequency of function of frequency. Resonance at 5 GHz is observed. The resonance frequency of the structure shifts to larger frequency when the coaxial feed is applied from the center of the circular patch. To lower the resonance frequency, it is necessary to enlarge the antenna structure or shift the feed point of the circular patch antenna. Coaxial feed used the the resonance frequency is 11.36 gigahertz, when the feeding point is at the center, it is the center, the circular patch antenna. In this study, the coaxial feed point is shifted in order to obtain resonance at 5 gigahertz without enlarging the circular patch size. The variation of the resonant frequency with respect to the feeding point is shown figure 7. The feed point is shifted radiusively from the center of the circular patch antenna to obtain resonance at 5 gigahertz. At the same time, gain enhancement for about 45% at resonance frequency is obtained by positioning the feed point at a radiusively distance from the antenna center. The antenna has 6.81 dBi gain and 78% total efficiency in this form. Three-dimensional gain pattern is given figure 8. SRR unit cell displaying left-handed metamaterial characteristics are arrayed to increase the efficiency and gain of the structured patch antenna. The array SRR unit cell is placed in according with the antenna size, and the metasurface all-textile antenna is obtained. All-textile metasurface antenna with 4x1 and 4x2 linear arrays of SRR are given figure 9. Figure 11 shows that when the left-handed metamaterial SRR arrays is placed on both sides of the circular patch, the power density increases and 3 dB beam width narrows in the phi equals 0 degree plane. It is observed that the gain increases as the beam narrows, even creating a single linear array to metasurface on the antenna increases the antenna gain. In table 1, efficiency comparison of all textile antenna is given. It is shown that the antenna efficiency increases 7.7% by using the metasurface antenna with 4x1 linear array, and the antenna efficiency increased 21.5% by using the metasurface antenna with 4x2 linear array. However, both metasurface structure significantly increases the antenna gain compared to the non-metasurface antenna. The metasurface has slight effect on the bandwidth of the antenna. The design has increased the bandwidth of the circular patch antenna. Comparison of the proposed antenna and some other all-textile antenna is given table 2. The proposed metasurface all-textile antenna has higher gain, higher efficiency, and smaller size compared to other all-textile antenna implemented in the 5 GHz band. A new textile, its conclusion, a new all-textile washable metasurface antenna design is proposed. The 2 different metasurface arrays were created and placed on the antenna surface to both sides of circular patch. The antenna cover WLAN, WBAN, and 5G application at the 5 GHz frequency. Simulation results of metasurface antenna are compared with the one without metasurface. It has been observed that the metasurface structure significantly increases the antenna gain and efficiency. It is low cost, ease of fabrication, high gain and efficiency characteristic. The proposed antenna can be used in wireless body area network and 5G application. Thank you very much for your attention. If you have any question you would like to ask, I will be happy to answer them.
Thank you for presentation. If any, we can take some questions. Seems to be not. I can ask you. You have used several number of antenna arrays. 1, 2, and 4. Is it possible to increase the number of antenna arrays?
Sorry?
Here you have used, in A, you have used 2 array, twin array.
Mm-hmm.
And in B, you have used 4 array. I ask if you can add more arrays.
Yes. I try this. I try this, but I want to fabricate this antenna. Yes, it is very high efficiency. High SRR is a high efficiency and high gain. But I want to fabricate this antenna. It is I want a easy fabricate. Therefore, only 4 times 2 linear arrays. I tried this. But
I see.
yes.
Maybe you can use a bigger plate.
Maybe.
Maybe.
I can try. Thank you, Professor.
Thank you for presentation. Now, this turn for the paper. It is entitled Wideband Enhancement of a mmWave Conical Antenna with a Metamaterial lens. I suppose it will be presented by Nesem.
Thank you, Professor. I'm sharing.
You can continue. We see your screen.
Okay. Can you see my presentation?
Yes.
Okay, thank you. Welcome to my presentation. Hello, everyone. My name is Nesem Keskin. I'm a PhD student in Yıldız Technical University and study with my professor Nurhan Turker Tokan. And also I'm working at R&D department of Prof and Communication Technology. And our presentation is about wideband gain enhancement of a mmWave conical horn antenna with a metamaterial lens. So you see,
excuse me, Nesem, if possible, can you open your video? If it's possible.
Also, unfortunately, my camera is not working.
Okay.
I'm so
then
sorry.
Then go on.
Okay, thank you. My presentation content include the first one is abstract, and I will give some information about introduction, and the second one is epsilon near zero metamaterial. Third one is a design of a horn antenna with epsilon positive, epsilon near zero metamaterial lens, and the fourth one is simulation results, and finally we can talk about the conclusion part. And firstly, in this work, metamaterial lens concept is applied to mmWave conical horn antenna. A metamaterial lens consists of 2-layer grid wire metamaterial with epsilon positive and epsilon near zero region. And the designed antenna is numerically investigated with a full wave analysis tool. The results show gain increase up to 2.2 dB within 72 between 86 gigahertz frequency band compared to traditional conical horn with the same physical size at 79 center frequency. An asymmetric epsilon positive, epsilon near zero region is chosen to reduce reflections. The operation of the flat metamaterial lens is based on the phase compensation concept, and the aperture mainly consists of two grid region. The phase shift inside the metamaterial with epsilon near zero characteristics is smaller compared to phase shift variation in the free space having epsilon positive characteristics. When electromagnetic wave coming from the horn antenna meets these regions, some part of it interact with the epsilon near zero region. The wave propagation along the horn axis continues its path in free space. The epsilon positive gap and the structure of the metamaterial lens are designed to obtain uniform phase distribution at the aperture of the horn. This technique improves gain characteristics significantly over a very wide band. And then the grid wire-based material unit structure having epsilon near zero operation consists of two grid wires, I said. And you know, Maxwell equations are given, equation 1 and 2 can be used to define behavior of the fields in the epsilon near zero region. Here, magnetic field is a curl free vector. Besides, by using equation 1 and 2, Laplacian of electric field can be derived. This is a result of static like distribution of the electric field in such a medium. And the electric field magnitude inside the ENZ region is infinitely large compared to the adjacent regions, and it can be given the equation 3. You see that epsilon A and electromagnetic field A are the electrical permittivity and the electric field of adjacent regions. And the equation shows that the electric field would have an abrupt rise when the electromagnetic wave enters to the epsilon near zero region with epsilon near zero. And if we considered an infinitely extended the planar slab on y plane with the metamaterial thickness at z equal to 0 and illuminate it with a linearly polarized normally incidence plane wave, the transmission coefficient can be defined equation 4. And you know the wave number in metamaterial slab K, and the reflection coefficients and the transmission coefficient, and z equal to 0 and z equal to also the metamaterial thickness boundary. And the other slide, phase distribution of the transmission coefficient is given there. Here mu epsilon near 0 equal to mu 0, and different cases of epsilon near 0 are observed. And you can see black solid line demonstrated the phase variation of the free space. It is clear seen that the phase shift inside the slab is lower than free space, and it gets even lower values for smaller volume of epsilon near 0. And the phase velocity of the wave propagation in the outer region of the metamaterial lens, namely slab, is slower than the wave propagation in free space. And you can see the velocity of the wave is given equation 5. This concept has been used to get uniform phase distribution on the aperture of the conical horn antenna. Then we can talk about the unit cell, unit structure of the two-layer grid wire metamaterial top view on the left side and the perspective view on the right side. You see the unit cell of the material, the structure has two grid conductor wires separated by a distance of 2.3 millimeter. And also the wire are in square form and having width and length equal to 0.1 millimeter. And you see the equivalent electrical permittivity of the unit cell can be defined by using Dirichlet model. And this is important to plasma angular frequency, and the operational angular frequency ratio is equal to 0, close to 0. Epsilon R will be very close to 0. At this operating frequency, we expect to see a rise in the gain of the antenna. This work is not by trial. I wrote a code to calculate a distance that should be between the thin grids. And CST microwave studio is used to analyze the two-layer grid unit cell. And the analysis is carried out under normal and oblique incidence. Perfect electric and magnetic boundary conditions are chosen in this simulation. And you see the plane cutoff view conical horn antenna. And the design of conical horn antenna is shown there. The conical antenna design parameters are given the E-plane cut view. The 10 lambda horn antenna with L length is given with the blue dash, you see. The 5 lambda horn antenna is shown with the black solid. The red solid line shows the two-layer grid wire metamaterial part with D thickness. With the propagation of the electromagnetic wave along the antenna axis, the phase distribution is distributed due to the side walls of the conical horn antenna. In order to achieve a homogeneous distribution, a metamaterial grid wire structure with almost zero relative permeability is added to the aperture of the conical horn antenna. So it acts as a lens to focus the energy, and this structure is a metamaterial structure consists of the two regions. And you see the standard waveguide aperture in this slide, and the horn aperture diameter is 23 millimeter. And therefore, by adding conductive wires to the antenna aperture, a lightweight and compact conical horn antenna is obtained. And the other is a homogeneous phase distribution is obtained by placing a material lens consists of a conductive thin grid wire unit structure in the aperture of the conical horn antenna. And the phase shift in the ENZ region is lower compared to the free space. Therefore, the phase velocity in that area is higher. So a structure with a higher gain and the directivity with a more uniform phase distribution is obtained. And you see the effective permittivity variation starting from the side walls of the horn is given the left side, and the free space relative permittivity is shown with a red dash dot line. And the angular variation of the metamaterial structure with thickness D, and although the curve changes the little for angle for theta small than 10 degree, it goes up quickly after that. Epsilon metamaterial is greater than the free space effective permeability when theta is bigger than 16.5 degree. The other is you see the left side in a plus shaped opening. The opening is created in the middle of the thin metamaterial structure. Due to the phase discontinuity, it is cut gradually from the corners closest to the antenna opening. The distance between the middle span of the structure is shown there. And the dimension of the other layer are downside according to the slope of the horn using these formulas. And for simulation results, you see the conical horn antenna, ordinary 5 lambda horn antenna, and the 5 horn antenna with epsilon positive, epsilon near 0 metamaterial lens. Reflection coefficient of the 5 lambda horn and 5 lambda horn with metamaterial lens and 10 lambda horn is shown the right side, the reflection coefficient. Reflection below minus 10 dB is observed in the band of 72 between 86 gigahertz for 3 antenna. And the reflection coefficient is larger compared to other due to the presence of metamaterial lens. Gain of the 3 antennas are given there as a function of frequency. Gain enhancement of the horn with metamaterial lens is clearly observed, although it is at 1 dB levels at lower frequencies. It gets about 2 dB at larger frequencies of the band. And so you see 3D gain patterns also. A 5 lambda horn antenna gain is 20.8 dBi, and the 5 horn with metamaterial lens at 79 gigahertz, the gain is 22.2 dBi. And the last one, the 3D gain pattern of 5 lambda horn with metamaterial lens are lens at 79 gigahertz is demonstrates 22.2 dBi gain is obtained at this frequency, and side lobes are below 25 dB main beam, and copolarized gain pattern of the 5 lambda horn with metamaterial lens and the 10 lambda horn at 79 gigahertz is given in E plane and H plane. Blue solid line you see belongs to 5 lambda horn, whereas red dashed line belongs to 5 lambda horn with metamaterial lens. At 79 gigahertz, 1.6 dB gain enhancement is obtained at the main beam direction. And finally, conclusion, the antenna is analyzed with a full wave EM tool, which is CST Studio Suite. And this antenna may be a good solution for the application such as satellites, radar, and remote sensing, where directive antennas are required. And also horn antennas are widely used for these applications, and they have a major drawback, bulky and heavy structure. And in this work, we propose a method to enhance gain of the horn antenna with a small size. A two-layer grid wire metamaterial structure consists of two regions with epsilon positive and epsilon near zero characteristics is proposed and applied to a conventional conical horn antenna. And this is my PhD. My main work is millimeter wave radar antenna systems in PhD. Although this is my first work, I have made many improvements. Actually, my suggestion is that it is possible to increase the gain by half by adding 3 grids. And I tried in the pyramidal horn antenna I made later. I achieved a 3 dB gain increase with a small size. And finally, I would like to thank you all the references that helped me realize my work. Thank you for attention.
Thank you for presentation.
Thank you.
If there's any, we can take some questions. There seems to be no. Then I can ask you a question. Maybe I have missed the point. Did you measure? Did you have any measurements?
Measurements?
Measurements.
These measurements now.
You have only simulations. I see.
We can get the gain enhancement is 1.6 dBi. But my suggestion is that it's possible to increase the gain by half by adding 3 grids. In this study, I used 2 grid wire. If you want to increase the gain like 3 dB, you can get adding 3 grids.
No. I asked if you have measured anything in the laboratory.
No. I'm not fabricate this work, but
do you think about it?
Yes, I did. I have made the improvements for the pyramidal horn antenna, not conical, pyramidal horn antenna. I worked it and I achieved a 3 dB gain. But I didn't fabricate this conical antenna.
Okay, I see. Thank you. Thank you for answers.
Okay, thank you very much.
Thank you for presentation again. Now our 5th and last paper entitled A File Transfer Method for RF Transceiver Modules Used in Internet of Things Applications. It will be presented by Gülden Günay Bulut. Please.
Okay, thank you. Greetings, everyone. By the way, are you able to see my screen?
Yes.
Okay. Greetings, everyone. My name is Gülden Günay Bulut, and I am a research assistant in Nevşehir Hacı Bektaş Veli University at the Department of Electrical and Electronics Engineering. And today I'm going to present a paper which is entitled A File Transfer Method for RF Transceiver Modules Used in Internet of Things Applications. Before I start my presentation, I want to talk about a little bit about the content of this paper.
Excuse me, I see 6 references. Maybe the wrong slide.
Sorry?
I see 6. The slide number 6. References.
Oh, but
Okay. Now correct. Okay.
now it is okay?
Go on. Okay, go on.
Okay, before I start my presentation, I want to talk about the content of the presentation. First of all, I want to make a small introduction, and then I will be presenting the file transfer method that we have realized, and I will be mentioning the theory of method, implementation of method, and lastly, I will be talking about experiments and results, and I will make some conclusions, and then I am thinking to finish my presentation. First of all, I want to mention a little bit about Internet of Things applications. As many of us know, Internet of Things applications are so popular and widely used nowadays. IoT is the abbreviation of Internet of Things and can be explained as the communication network which physical objects are connected with each other via larger systems and via internet. So I can say that in Internet of Things applications, as you can see, there are smart devices which have their own antennas and they are connecting with each other via internet. In this case, they have to have a data transmission. So in this data transmission, generally, a small amount of data transfer is sufficient and generally used for sensory information transfer. However, in many cases, in some cases, in the contrary of the simple applications, the file transfer procedure requires more transactions, which is in like our study. In simple communication systems, which small data transmission is carried out, information transmission is only...
Excuse me. We can only see number one slide.
Sorry?
Only we can see number one, slide number one. We cannot.
I don't think that it's a problem because of me. I don't know. What's your recommendation about this? What's your suggestion? How can I? Should I start
again? You can share again.
Okay, let's try to share my whole screen. And how about now?
Yes, I can see.
Okay.
I think it's okay. Go on.
In the simple communication systems, which small data transmission is carried out, information transmission is only protected by a simple confirmation message, while the security of the file transfer producer in an RF communication system is provided with a series of transmission rules. In this study, basically, we recommend the general file transformation method for RF transceiver modules, which can be used in IoT applications. Basically, we use NRF24LO1 unit, and it's a very handy RF module for IoT applications. In a nutshell, if I had to summarize our study, we proposed a file transfer method for the transceiver modules, which are suitable for Internet of Things applications. And we have created a general set of rules which explain for a safe wireless file transfer. And lastly, we realized a test environment without a line of sight, and we got some results. And now I want to mention about our file transfer method. For file transfer method, we have created a scenario. In this scenario, we have three main actors, which are transmitter, transmission medium, and receiver. As you can see in the figure, we have our transmitter, we have our transmission medium, and we have our receiver. In this scenario, as transmission medium, we use air. So we can say that we use wireless. In this scenario, also, our transmission signal is propagating through the air in a three-directional wave. So, because of that, the signal is passing through the air. There might be some lost packets. The information signal is generally attenuated by obstacles or noises which is coming from outside. So, in this case, we are trying to, actually, we proposed a method to block this, to terminate this situation. So we For this transformation, we created a set of rules between transmitter and receiver. So now I want to talk about this diagram. So our transformation process begins with the transmitter. Transmitter sends information signal to receiver to notify that the transformation is about to begin, and also it sends to receiver an information which is about the file size of information. And then receiver creates an array for the incoming file, and then the transmitter sends all of the transformation signal to receiver as a burst, and then receiver starts to take all of the information with their sequence numbers and put them into the array that it's created before by their sequence numbers. And then receiver starts to ask about the transmitter about is that there is any lost packets. If there is not any lost packets, the transmission is complete. If there are any lost packets, it sends the information of sequence numbers of lost packets to transmitter, and then this process continues in a loop like this. Of course, in case of the transformation is failed, we have a time counter in our transferring program. So it basically counts the time. And if the time is over, the transmission process will be shut down. And now I want to talk about our implementation of method. As you can see in the figure, we have two main units, which are called transmitter and receiver. In transmitter unit, we have our Yagi-Uda antenna, we have our Arduino mega controller, LiPo batteries, and our SD card. And in our receiver unit, we have our U-slot antenna and our Arduino Nano microcontroller. The transformation process begins when the user presses the starting button. And in this implementation, we were trying to pass a lake picture from transmitter to receiver. Yeah, I can say that, basically say that. And now I want to talk about our results. During our experiments, I want to go back to this slide. During our experiments, while our receiver was sitting on the top of a desk, we have changed the position, the direction of our transmitter in 12 different ways. I mean, we have changed the direction of the receiver in 3 different directions. Also, we change its direction through the azimuthal plane. So in total, we change its direction in 12 different ways. So you can see in the table our positions. So we have basically, obviously, 12 different directions, and we count the transmission time. So I can say that the best experiment was the best result occurred when the receiver was in B5 and A1 position. The worst results achieved when the receiver was in the B7 position. So I want to make a few conclusions. As you can see, the method proposed in this paper is designed to handle the lost packets occurred during the wireless file transformation. And also we tested our method with a set of experiments. It contains none of line of sight propagation. As I told before, there were obstacles between our receiver and transmitter, so we can say that it was a non-line of sight propagation. And finally, according to results of the experiments, the file transfer method proposed in this paper, it can be easily applied to any IoT applications. Besides, this work was supported by the Scientific and Technological Research Council of Turkey under grant number 12OE 296. And these are obviously my references. Thank you for your courtesy of listening. Any questions?
Thank you for presentation.
You're welcome.
We can take questions if there is any from the participants.
Well, actually, sorry if I'm interrupting. I want to ask a question to paper second paper, but I think she's not here. Right?
I am looking. She's not here.
Actually, I
She's gone.
wanted to raise my hand, but I think you didn't realize while I'm doing it. So, anyways, thank you.
Then I can ask you a question. I see that I see that you have used 12 positions.
Yes, in total we
positions,
have 12 different directions. Yes.
Yes. But I think it's not a big number. It's less, isn't it?
I think it's enough for our experiments because the transformation is successfully achieved and also lost packets successfully saved. But of course, as you can say that we could also try different directions. But as I think and as my advisor thinks that 12 directions are also enough for a paper like this.
Maybe. But if I were you, I would think that I would increase the number of positions, and I would use statistical methods.
Yeah, okay.
Statistical methods.
I will
maybe
take note of this. Yes, thank you.
Okay, thank you.
Thank you for your
presentation.
comments.
Thank you for presentation.
You're welcome.
I think we have completed the session. I would like to thank to participants and guests for their participation. Okay, I think we can complete the session. With my best regards.